Okay, I want to take a few minutes and I want to talk about what I cover in Unit 3A, which is the force aspect of when there is an unbalanced or a non-zero net force acting on a body. Now, it might seem a little silly, that it might seem obvious what the force aspect is, but we're going to look at all the, I don't want to say consequences, but everything that results from only the force aspect with this situation. We'll look at the energy and the momentum aspects separately, and we're only looking here at forces. So the first thing that comes to mind is that if we have an acceleration, that is equal to the net force over mass, which is just Newton's second law. This is what we're dealing with. If this is non-zero, we are always going to have a mass. Be a little careful. This M technically refers to inertial mass, the mass of a body that resists a change in motion. There is also another type of mass that an object has called gravitational mass. We'll get into that a little bit later. These two terms are not necessarily the same, even though we treat them the same, and so there can be there's always a little confusion that arises from that. But this M, mass, technically is inertial mass. And then we have this acceleration. Now, this is Newton's second law. A lot of times we simply write F equals ma. Quite honestly, there's nothing wrong with that. However, when you write F equals ma and you get used to writing it like that, sometimes you start thinking that force is the result of an acceleration, and that's not the case. Newton's second law tells us that the acceleration comes from this unbalanced force. So it's important to recognize that we first have a force and then we have the acceleration. And sometimes you miss that in F equals ma. And so I like to tell the kids there are two definitions for acceleration. It's the result of a net force, Mathematically, we calculate acceleration as change in velocity over change in time, or the fancy words, the time, rate, and change of velocity, or the unfancy words, how fast velocity changes. It's a common misconception when first introducing Newton's laws that kids want to say that force causes motion, and that's not correct. Force does not cause motion. Newton's first law tells us that a force causes a change in motion. Very important difference between motion and a change in motion. The same idea here is true between acceleration and velocity. Acceleration and velocity are two different things. Acceleration results from a change in velocity, not from the velocity. So it's real important to understand the difference between acceleration and velocity. I'm going to talk about that a little bit more in just a minute. Before I do, though, I want to look at the units for acceleration. We know the units for velocity is meters per second. Our units for time is seconds. So our units for velocity, our units for acceleration are meters per second per second. Every second, our meters per second is changing. That's what acceleration means. How fast every second is our velocity changing? Is our meters per second changing? And so even though, and so I like this idea, I like writing the units like this when first introducing acceleration to instill it is meters per second every second to help differentiate between velocity and acceleration. However, we will end up writing this as meters per second squared because that's how the units work out. And so while I know this is acceleration, and while I understand what the units acceleration are, and I use this myself, when I first introduce acceleration, I like to call it meters per second, just to instill the idea that acceleration is different than velocity. Let's take a second and look at the vector aspects of all these terms that we've been dealing with. And so let's just list all the terms that we have encountered so far. We have encountered x, which is position, delta x, change in position or displacement, velocity, acceleration, time, force, and mass. And one thing that's important to keep in mind and to recognize is terms that are vectors, terms that are scalars, because it's a vector, it has direction associated with it. And I don't want to say that has special rules, but that does have different applications. So things like mass, time, position, these are all scalars. They're just a number. They have no direction associated with them. Fine. But because acceleration is net force over mass, force is a vector. There's a direction associated with the force that when you apply something. Acceleration is also a vector. And these two vectors are in the same direction. Real important to understand that when we apply a force to something, it's going to be accelerating in that same direction. I'm going to talk about that a little bit more in just a second. Velocity is change in position or displacement divided by time. Change in position, displacement is a vector. We move so many meters in a certain direction. That's a vector, which means velocity is a vector, which means velocity and displacement have the same direction. Acceleration, and so velocity is also a vector. Acceleration is change in velocity over change in time. We know acceleration is a vector, and we know time is not a vector, which means change in position is a vector. There's a direction associated with that. We normally don't use that direction. We normally don't say the change in, I meant to say change in velocity. We normally don't say the change in velocity direction, but what I want you to understand, and the reason I'm writing this, is that acceleration and the change in velocity are related. And so I'm going to write this as acceleration and delta V are related. I'm not necessarily saying that, I'm avoiding saying they're in the same direction because delta V, we don't usually treat that as a vector. They are related. What you are not seeing is that acceleration is related to velocity. It is not, and that's an important thing to keep in mind. Let me take a quick look at that. Let me clear my board and let me take a quick look at this at that, because that's an important idea to recognize. Okay. All right. Let's say we have a car on the road. I know it's not the greatest car. And let's say the car is moving that way. And so if it's moving that way, its velocity is to the right. If its velocity is to the right, if it's moving that way, then its displacement is to the right. Fantastic, wonderful, love it. Let's say we then give the car a push to the right. We know that the direction of the force of that push, and we know the direction of the acceleration are in the same direction, so it's also going to accelerate to the right. So the question is, what's this car going to do? It's going to speed up. It's going to go faster because this force caused a change in motion. This force caused a change in velocity. Why or how? From this acceleration. It's going to speed up because accelerate. Now, I just said the direction of acceleration and the direction of the velocity are completely unrelated. And I'm still sticking with that, even though it might sound like I'm contradicting myself. Let me get through this whole example, and then so I'm gonna skip this for right now. Let me finish my other example. Okay, we got a car. We got the same car. It's going in the same direction. We have a velocity, we have a displacement. This time though, I'm going to apply a force in the opposite direction. Maybe I'm pulling back on it, I don't know. And then I have an acceleration in the opposite direction. What's this car going to do? It's going to slow down. So this is what I want. This is what I started talking about here, and I wanted to wait. I just said that acceleration and velocity, these directions, these terms are unrelated to each other, and they are. That doesn't mean we can see some relationships between the two. In this case, acceleration and velocity are in the same direction. And when acceleration and velocity are in the same direction, it's going to speed up. A and V, same direction. Whether acceleration and velocity are both positive, whether they're both negative, it doesn't matter. The object will speed up. It'll go faster in the positive direction, or it'll go faster in the negative direction. Here, velocity is that way, acceleration is this way. They're opposite. A and V are in opposite directions. And when they're in opposite directions, the object will slow down. It doesn't matter which one is positive or negative, it will slow down. And so while the acceleration and velocity are unrelated, there is a relationship between the direction of acceleration and direction of velocity. If they happen to be in the same, and if that's kind of confusing to you, don't think about acceleration. Think about if velocity is that way and we have a force, an unbalanced force in the same direction, I think it makes sense that it's going to speed up. Well, force and acceleration are in the same direction. And if we have a velocity in that direction, but we have an unbalanced force in the opposite direction, I think it makes sense it's going to slow down. Boom. This is all the philosophy, the ideas behind, I shouldn't say philosophy, this is all the ideas, the concepts behind an unbalanced force acting on an object. Let's take a look at the math. All right, let's talk a little bit about kinematics. And I like to introduce this word by asking, what's it mean? And of course, but they do know. They know kine means moving. They know matics, I don't know. They might take a guess and think, oh, that sounds like mathematics. And I go, perfect. This is the math behind an object moving. And that's all it is. And what kinematics does is, kinematics is a series of equations that we have that relates an object's position with its velocity, with its acceleration, and with time. And it just relates these four variables. the first three equations on the formula sheet are the kinematic equations. And so I'm going to write them as they are written there, and we're going to talk about them. And I always get some of these terms mixed up because I usually write them with a few shortcuts, which are perfectly okay once you understand what the shortcuts are. So those are our kinematic equations. Now, a couple of things to be careful about. Obviously, t is time. A stands for acceleration, but we have the subscript x there to say it's the acceleration in the x direction. So that subscript x for acceleration and velocity tells us there's direction to it, tells us that it's a vector. I don't always write the subscript x. If I know we're moving horizontally, I leave it off. If I know we're moving vertically, I leave it off. And we'll talk about that in just a few minutes. The subscript 0 for the velocity and position refers to its initial. And so this is the initial velocity in the x direction. This is the object's initial position, initial x position. And then my final terms here are more or less its final velocity. I guess there should be an x right there. This is the quote-unquote final velocity. Some people, instead of saying initial and final with a naught and with a basically nothing, they would put an I here for initial, they would put an F here for final, and that is perfectly okay. That works 100%. People understand how that is. And so, like I said, I normally don't put the little subscripts x there because we're going to be doing a calculation that's either in the horizontal direction or in the y direction. And I guess let me take that statement back a little bit. The only time I put the little subscript as to its direction is when we're doing projectile motion problems, which I introduce in unit, I forget what unit it is, it might be unit 5. So I don't even get into that quite yet. So that's why I don't even bother with the x subscripts right now, because the problem is either horizontal or it's vertical. About the only thing I do differently when I write these equations, and you can do it this way, is I don't say x minus x naught, I say delta x. And then for this equation, and I'm going to write it up here, basically if you bring this x naught over, you have x minus x naught. Well, that's delta x, our position. And so I usually write these two equations not with the x and the x naught, but as a delta x expression. So the big rule with these three equations, and this is the thing you got to keep in mind, and in a little while, in a few months, we're going to get to a situation where we can't apply these. But the big rule is the acceleration must be constant. And so in this case, I'm going to say AX must be constant. If it's not constant, we cannot use, I can't spell, we cannot use these equations, or we have to break them up. For example, if an object is starting from rest, it begins to have an acceleration, a constant acceleration, and then goes at a constant speed. We got to break that up into two parts, one where there's a constant acceleration part, one where there's an acceleration of 0. And so we can use these, but we'd have to break it up. But if the acceleration is changing always, then that's a different issue, and we can't use that. We'll come across that later on, unit 7 or 8, I think. I really don't even remember. That's in a while. So we've been talking about kinematics. I just looked at the kinematics and the three kinematics equations. When the object is moving horizontally, I want to look at a different aspect, and I want to look at an object that's moving vertically. And for this, we're going to call this free fall. And basically we're only looking at straight up and or straight down motion. That's it. We will look at something that's being thrown through the air later on. That's a projectile motion. A couple of things. We are still dealing with the four, I think I listed 4 variables, except I'm not going to call it X because that's what we did before when we're talking about horizontal motion. We're going to have Y. And so we have its vertical position. We have a change in vertical position. We have velocity that's in the Y direction. We have acceleration, and we have time. And so we're going to be using basically the same variables. The difference is on those 3 equations, I'm going to change all my X's to Y's. That's fine. No issues there. The other change I'm going to make is I'm going to change acceleration, because normally an equation might be written as Vy, my final velocity in the Y, is the initial velocity in the Y plus acceleration in the Y times t. Fine, there's nothing wrong with that, except I don't write acceleration in the Y direction. We designate that when we're dealing with free fall as g, the acceleration due to gravity. Be very careful. Do not call it gravity. When we call something gravity, we're implying it's a force. This is not. This, g, is an acceleration that is due to gravity. Now, and it takes the number. Use the number. I know this technically is not the number. The number technically is like 9.8. We use 10 meters per second squared. And it's very important to use 10. I shouldn't say very important. If you use 9.8, that's fine. But any type of problems, multiple choice questions, if they use a value for g, they're going to use 10. And a free response, use 10. It's perfectly fine. This is physics. And I know this might sound a little bit absurd, but the accuracy of our answer is less critical, less important than how we got there. In this course, we're interested in how we got to our answer. And if we're off by a couple tenths, that's perfectly fine. Nobody cares. Now, so let's designate a couple of things when we're doing horizontal motion. And so let me just kind of clarify that for horizontal, we have to recognize that velocity and acceleration and displacement are vectors. And so what we do is we say if it's moving to the right, that's a positive direction. If it's moving to the left, that's a negative direction. Okay, that's fine. I think it's a little bit sad that we are connotating left as negative, as bad. For us left-handers, that's kind of sad. But anyway, I can't complain a whole lot. This is our general convention. If we don't know the direction, we just say the direction the object is going is positive, the opposite direction is negative. For vertical motion, though, it's a little bit easier. If it's going up, that's a positive direction. If it's going down, that's a negative direction. So when we throw an object up in the air, initial velocity will be positive. It goes up in the air, it stops, it comes back down. As it's falling down, we now have a negative velocity. If we throw something up in the air, gravity is always pulling it down, which means the acceleration due to gravity, which is in the same direction, is down. And so we have to designate this with a negative sign. This does get a little confusing because there's other times when we use g, we don't put in the negative sign. And so what I like to, my general rule is for those kinematic equations, that's when g is negative because we're using it as a vector. Any other time, we don't put in the negative sign. So a couple of things about vertical problems that it's important to keep in mind. And I'm going to make these notes over here because I'm running out of room. Let's see, acceleration in the y is always g, which is negative 10 meters per second squared. The velocity in the y is 0 only at the top. In other words, you throw something up in the air, it has a positive velocity in the y direction. It goes up in the air, slows down, comes to a stop, falls back down, hits the ground. Right here is where we have a 0 velocity in the y. That is the only place. Kids want to think, oh, when it hits the ground, it has no velocity. No, we're always talking about the velocity right before it hits the ground. At the peak is the only place where the y velocity is 0. Always take this rule with you to projectile motion. It'll help you out there as well. Keep in mind on the kinematic equations, and if I could flip back, let me try that. Let's flip back real quick and look at the kinematic equations. Cool. Did you see that one with the squared? When you take a square root of an answer, the square root gives you two answers. It gives you a positive and a negative answer. The calculator only gives you one, the positive. So be very careful. And so I'm going to write it as square root has two answers. If we're using that third kinematic equation, and we have to take the square root of the velocity, we're going to get two answers, a positive and a negative. And so you have to decide which one do you want. If you're finding the velocity as it's going down, we want the negative answer. And so just be really careful about that. Okay, that's what I got for Unit 3A. There's another aspect that I cover in class which deals with the relationship between position, velocity, and acceleration graphs. But I'm going to do that with a, I have that with a separate video because that's a pretty big idea. Until then, good luck.